Rats. I've read through this thing like 3 times. I understood it last time I read it, but it will take me longer than a minute. So there's this. This proof is on page 31. Then theorem 1.9 is also very interesting. It says every continuous path, listen to me, map, from the 2-disk to the 2-disk has a fixed point. That is, well, we know what a fixed point is, right? Talked about that a fair amount in here. And the argument for this is pretty cool. You know, it's a proof by contradiction, and essentially he shows. Well, let me just draw a picture. He draws this picture, right? If this is h of x, right? Okay. And if there's no fixed point, right? Then, and so D2 is the 2-disk, right? If there's no fixed point, that means x is not the same point, right? So maybe it's here. So what can you do if you have 2 points which aren't the same? You can draw a line through them, right? So you can go from h of x to x, and then somewhere it hits here, right? So this defines a map from D2 to S1, right? And not just that, he argues that it's clearly continuous because if you perturb x a little, if you mess with x a little bit, that would also mess, like perturbing either one of these a little bit perturbs the other a little bit. That's essentially the argument for it being a continuous map that he gives. Hey, if he gives it, I can give it. So he says that this is, and he calls this mapping R. And so, like, what happens if we restrict R to S1? Would that give you a chord? I don't know. Huh. Yeah. Well, I guess he doesn't. I should be careful. He didn't say this directly. He said something a little bit different. Let me see what he says. So he says R is a retraction of D2 onto S1. All right. R is a retraction of D2 onto S1. Well, he claims that R of x is equal to x for x in S1. Is that clear? Oh, well, yeah, duh, by definition, right? So, yes. All right. Blowing my mind, but yes, obviously. And so that means it's a retraction, right? And so he says if F naught's any loop in S1, then in D2 there's a homotopy of F naught to a constant loop. For example, the linear homotopy. And since the retraction of R is the identity on S1, says the composition R f of t is then a homotopy in S1 to the constant loop at x naught. So basically, let me just get to the point here. So this implies that there is a homotopy of a loop in S1 to the constant constant path class, right, in D2. But that's absurd because, of course, that would then say that every loop in the fundamental group of the circle is homotopic. But they're not, because there's as many of them as there are integers, right? And they're different. So this would imply the fundamental group of the circle is trivial, but that's not the case. So that's a contradiction. Therefore, there must be a fixed point, and then you can't set up this retraction. So it's a quite beautiful argument. And he mentions that this was first proved by Brouwer around 1910, not using the idea of homotopy, but using something called the degree of maps. And then he quotes a couple of more grown-up versions of this theorem, namely, for every continuous map, if you have a continuous map, so these are good to know about. If you have a continuous map from the two-sphere, to R2, what can you say about it? What does it have? It has a pair of antipodal points. At least one pair of antipodal points. With, f of x equals to f of minus x. And so this is actually the Borsuk-Ulam theorem. Well, the two-dimensional version of it. There are higher dimensional versions. In fact, he mentions that it holds for maps from Sn to Rn. Okay. And he goes on to explain a proof of it. Let's see here. Where was I? Let's see here. So one other, well, maybe I just have to admit defeat. There's a little bit more I wanted to tell you guys about homotopy. So the next thing, well, actually, how much more time do I have today for you guys?
Negative 4.
No, but how much more time do you have today?
Similar. I don't know how far away at 6.
At 6? You don't know how far away?
I could check the address. Someone else can give me a ride.
Someone else can give me a ride. All right, we'll stop here. I guess I'll pick back up again next time. But
6 o'clock milestone.
yeah, I have a few more fun facts to share with you guys, but I will stop here for now. Oh man, I only got an hour and 8 minutes into it.